So we're going to start with a two-dimensional representation of the Klein 4 group.
I remember this.
And we'll do it as though it were the symmetries of, I don't know, an ellipse or something like
yes,
that.
Yes,
So
I remember this.
D2 of E.
I feel like I went through it so many times, just
Yeah.
the different reflections, yeah.
Yep. So there's the identity. And we want to see all these matrices explicitly in this example so that we have the feel for it. So then maybe this is reflection in the x direction.
As I've done with D2 of D3.
Yep. Then the B reflection would be maybe, oops,
Just
reflection in the y direction. And D2 of AB.
-1.
Yep, it would be reflection through the origin. So what I want to do is run a complete eigenanalysis on these four matrices. Figure out what are their eigenvalues and eigenvectors so that we can then figure out what they all have in common, which is really what we want to know. So starting with the first matrix, what are its eigenvalues?
Well, we would have, we would just have, we'd have lambda squared plus,
Lambda squared minus
lambda, let's see. So 1 minus lambda, 1 minus lambda, or
1 minus lambda times 1 minus lambda.
yes.
That's right.
Okay, so it would be, let's see, lambda squared, and then the, yeah, okay, so we would just have plus minus 1.
Not even.
Oh, just 1.
Just 1.
Mhm.
Right.
Yeah.
So there's only one eigenvalue for this matrix, one distinct eigenvalue. By the way, all these matrices are diagonal, so we can take our shortcut for diagonal matrices to find their eigenvalues. The diagonal matrices eigenvalues are the entries on the diagonal.
Yeah.
So, alright, so there's those eigenvalues. Let's just do all the eigenvalues first. So this representation for A has eigenvalues.
-1, 1.
Right, this one has the plus and minus 1, because it's a reflection. Likewise, 1 and negative 1, whatever order we decide to list them in.
And then just -1.
That's right, so this last one has only -1 as an eigenvalue. So there are all the eigenvalues. But let's also get the eigenspaces of these matrices in here so that we can then start to compare. If they share eigenspaces, then we should know about it. So one by one here, starting with our first matrix, what's the eigenspace of lambda equals 1, given there's only one eigenvalue in this example? What is the eigenspace associated with lambda equals 1 for our first matrix?
Wouldn't it just be the line y equals x?
Actually, it's even better than that. So let's just carry out the calculation where we solve for the lambda equals 1 eigenspace by finding the null space of A minus 1 times identity. But A minus 1 times identity,
because A is, yeah.
because A is the identity matrix, is the zero matrix. And therefore, what is the null space of the zero matrix? What vectors are nulled by the zero matrix?
Everything.
Everything, exactly.
So the whole, yes.
The entirety of the xy plane. So, you know, another way to look at it is if we find a parametric vector solution of this, both x1 and x2 are free. Okay? Both x and y, if you like, are free.
Yes.
So, that eigenspace associated with lambda equals 1 is the entire xy plane. So no two ways about that one. That's what makes it the identity matrix. Only the identity matrix has the entire xy plane as its lambda equals 1 eigenspace.
Yes, of course. Yeah, I would leave every vector the same.
Yep. So there's our first matrix. For the second matrix, what is the eigenspace associated with lambda equals -1?
Let's see. So we would have, well, for lambda 1 is for lambda 1. So
yeah.
Lambda is equal to -1. Okay, so we would have we'd have 0, 0,
right?
0, 1.
1 minus -1.
Okay, so
And so our free variable is
our free variable is x.
Is x. And y is bound to equal 0.
Mm-hmm.
So our lambda equals -1 eigenspace is the x-axis.
Mm-hmm.
Every vector on the x-axis is being flipped, reflected.
Okay. Oh, and this makes sense, yeah.
Meanwhile, the lambda equals 1 eigenspace what would that be?
Oh, that would be the y-axis.
It's the y-axis.
That remains the same.
It remains the same.
With a flip across the...
That's right. So we can do the rest of these just thinking geometrically, I think, rather than carrying out the algebra. So this...
It's just the opposite
lambda
case
equals
for
1
the vertical
x.
reflection.
That's right.
So that which actually is in... Well, the invariant would then be... the variant subspace would be the x-axis.
Right.
Then the vertical axis. Well, then... then everything that's not the y-axis, or
So lambda equals 1 would be here for this matrix, and lambda equals -1 would be that one for the third matrix. But then for the fourth matrix, what happens? What's the eigenspace associated with -1 for the last matrix?
so well, it would be the identity as well.
A plus I is going to give me
Oh, 0, 0,
the
0,
0 matrix.
So in that case, we get the identity. We get
The
the
entire.
whole.
That's right.
XY.
We get the whole xy plane has eigenvalue this time, lambda equals -1. So the original reason we started with the example is we wanted to talk about simultaneous diagonalizability. We wanted to know why it's the case that there is a basis for the xy plane that diagonalizes all four of these matrices at the same time. Well, it just so happens that these matrices are already diagonal, right? So it's even the standard basis does it, but paying attention, calling out the standard basis for playing that role is what we're going to do here. Is that what these eigenanalyses all have in common is that we can always consider the x-axis to be an eigenspace of every single one of these transformations. Oops. Because the x-axis here is an eigenspace of our first transformation with an eigenvalue of 1. It's an eigenvalue in the second transformation with an eigenvalue of -1. It's an eigenspace of the third transformation with eigenvalue +1, and it's an eigenvalue of the fourth transformation with eigenvalue -1. So in other words, if we want to build a basis to diagonalize all four of these matrices, we at least know that E1
something spanning,
or anything in the x direction, right?
Yeah.
1, 0 is an eigenvector of all four of these transformations. Its eigenvalue is not always the same, but it is always an eigenvector of each one of these transformations. And likewise for the y direction. So the y direction is an eigenvector with eigenvalue 1 in the first transformation. It's an eigenvector with eigenvalue 1 in the second transformation. It's an eigenvector with eigenvalue -1 in the third transformation. And it's an eigenvector with eigenvalue -1 in the fourth. But the point is that it's always an eigenvector. And so E2 is also part of a basis in which every one of these transformations is diagonal. And so to drive the point home, just observe that all these matrices are already block diagonal in the E1, E2 basis. It doesn't always happen, but it did the way that we constructed this, just because when we constructed this representation for this group, we thought about horizontal and vertical reflections, which are eigendirections, which have E1, E2 as eigendirections. If we decided that different reflections were how we were going to represent this group, then we wouldn't have necessarily gotten diagonal standard matrices. But we still could have come up with a basis in which those matrices were diagonal. And the entries on this diagonal just happen to be the eigenvalues. So here are the eigenvalues that the E1 eigendirection had for these matrices, and then there are the eigenvalues that the E2 eigendirection had for these matrices.
Well, I mean, as you said before in class, we can think of a linear transformation as just taking the taking the basis vectors linearly, transforming them, and taking those columns and those column vectors and putting it in the matrix.
Yep.
And that's how we can construct a linear transformation. So if we were to have, let's just say, for our identity representation, 2, 0, 0, 2, something like that.
Well, I wouldn't put that in the identity transformation, but if it were somewhere else, because we can never represent the identity by anything other than the identity matrix, if it's a representation. Right? It has to be a homomorphism, which requires. But okay, but just for the sake of argument, if we did this.
Well, I'm just thinking of like what if we had basis vectors that were instead 2, 0.
Oh, if our basis vectors.
Yeah, that's what I'm trying to say.
Yeah,
so the linear transformation.
The transformation
would
is still
be the
same.
Yeah.
Transformation is still the same, but our matrices would change. So we would be then representing, well, but 2 times E1, if E1 has eigenvalue 1, then so does 2 times E1 have eigenvalue 1. Right? That eigenvectors come in complete vector subspaces. Right? And so any linear combination of eigenvectors that have the same eigenvalue will also be an eigenvector with that same eigenvalue. So even if I change my basis by scaling it, I'm still going to get the same diagonalizations going down the line. The only thing I couldn't do, if I wanted to maintain block diagonal, is I couldn't then combine these to, say, do E1 plus 4E2 or something here.
Oh, and that makes sense because we were then thinking, again, of,
Right, that would change the direction of one of my supposed eigenspaces, and that wouldn't be what I wanted.
But if we were to kind of shift things over a little bit and then think of reflections in that way and that way, how would it change the picture?
Let's just rewrite these matrices so that instead of reflecting on the coordinate axes, we're reflecting on the diagonal lines y equals x and y equals minus x. So if our axes of reflection are different, the matrices now, the standard matrices, are not automatically going to be diagonal. Instead, the reflection that we see right here, a reflection across the line y equals minus x, is going to have the I think this is what it is. Actually, no, I'm not so sure about that. If I reflect across the line y equals minus x, then I need to preserve... maybe, no, this can't be it either. Let me think a little more carefully about this. So we need to preserve the line y equals minus x. So anything which has opposite x coordinate to its y coordinate has to stay put. Oh, why don't we do this a smart way? To find a standard matrix, all we have to do is transform the standard basis vectors. So if I take 1, 0, and I reflect it across the line y equals minus x, it ends up 0, minus 1. So that's the first column of this matrix. And then if I do the same thing with 0, 1, reflected across this line, becomes minus 1, 0. Oh, so I did have it. Okay, so there's the standard matrix for that reflection. And then the reflection across y equals x is that one. And their composition, oddly enough, is still diagonal, just like it was before. But, I mean, now we've introduced that complication, that we no longer have all 4 of these matrices in standard form are no longer diagonal. But simultaneous diagonalizability is supposed to mean that we can find a basis that nevertheless, in that basis, these matrices are in fact diagonal.
Yeah, which, well, one example is the standard basis.
Well, not in this example, it's not.
Well,
right.
oh,
because now my transformations are no longer oriented with respect to the standard basis. So I want to, nevertheless, find a basis in which these transformations are diagonal.
Okay, and well, if we just take, well, the vectors that would span those different axes now.
Okay. So we take, what would this be? 1, 1 might be a vector that lies in the direction of y equals x, and minus 1, 1 lies in the direction of y equals minus x. Then if we establish that basis, let's list it in this order, 1, 1 first, and then minus 1, 1 second. If that's my basis, then let's think about what these matrices are with respect to that basis. Well, the identity matrix, no matter what, always is the identity transformation always has the same representation, as long as our basis is the same in the domain and the codomain. And the same actually is also true of this matrix, because it's just minus 1 times the identity matrix. So that one's not going to change either. They began diagonal and they remain diagonal. So it's really just these two remaining ones that we have to figure out what are their expressions with respect to this new basis. So when I take and I apply this reflection, so d2 of a, applied to the first basis vector, which here is 1, 1, this reflection flips 1, 1. Right, because that's the direction that we're reflecting for this matrix. So it becomes negative 1 times itself plus 0 times the other vector. So the first column is negative 1, 0. Why? Because 1, 1 was an eigenvector of this transformation. So naturally, when I transform an eigenvector, I just get a multiple of itself, which is why that column is a diagonal column. I only get the negative 1 in that entry. So again, the reason is that, if you like, a times v1 is equal to negative 1 times v1 plus 0 times v2. Which is why this column is negative 1, 0.
Negative 1, oh.
Where v1 is that vector.
Okay.
And we'll call this one v2. And then when we do this with v2, v2 is also an eigenvector of a times v2, but its eigenvalue is positive 1. So we get a positive 1 here. And then we had none of v1. So we get a 0 up there. So in this basis, that matrix has become diagonal again. Because this basis is a basis of common eigenvectors to all 4 of these matrices, the expression of each of these transformations with respect to that basis is always diagonal. So simultaneously diagonal, if a set of linear transformations is simultaneously diagonalizable, simultaneous diagonalizability is equivalent to having a set of vectors which are eigenvectors for all of our transformations.
Okay.
And in this example, 1, 1 and minus 1, 1 was a basis that did that.
Mm-hmm.
Because each of those vectors is an eigenvector for every one of our transformations. That means we can write every one of these transformations with respect to that basis as a diagonal matrix.
Okay. That's why I suggested those.
Yep. So what are the algebraic consequences of simultaneous diagonalizability? So again, this one of my favorite terms in linear algebra, because it has so many syllables in just 2 words. Simultaneous diagonalizability.
Well, one thing that's nice is that having all of these diagonal matrices, well, in terms of the algebraic structure, preserves diagonalizability when you multiply 2 elements of this group of linear transformations.
Say that again.
So for this group of linear transformations, diagonalizability is preserved with the group multiplication.
The product of 2 diagonal matrices is a diagonal
Mm-hmm.
matrix.
Yes.
That's right.
Whereas before we had some being diagonalized, some being diagonal, some not. So.
Mm-hmm. So the fact that there's a common eigenbasis for all means that there exists a change of basis matrix, one change of basis matrix. Let's call it P. And let's let this be the transformation matrix from the eigenbasis into the standard basis. And so P is a matrix whose columns are this common set of eigenvectors. v1, v2, and however many we have. And so these are the eigenvectors. And the claim is that what simultaneous diagonalizability means is that there is one change of basis matrix such that if I take any old vector in standard coordinates, so let me just write that as x with standard coordinates, then applying this change of basis matrix, P, will now give me x in its eigen coordinates, and then x in its eigen coordinates, when one of these matrices acts on it, let's put an A here, that the result is supposed to be just a scalar multiple of x written in its eigen coordinates. So in its eigen coordinates, we just stretch our x. So here's what I think I'm trying to say, is that when we take x in its eigen coordinates, how do we stretch a vector which is in its eigen coordinates? We just multiply it by a diagonal matrix. So I'm going to put a diagonal matrix over here.
Matrix. Well,
achieves an eigen stretch, we're going to call it. But that we could achieve the same effect by multiplying the standard matrix A by the standard coordinates x, and then converting the result. So this is going to be the eigenstretch in standard coordinates, then convert that into eigen coordinates by multiplying it by p. So the eigenstretch in eigen coordinates.
and what's D exactly here?
D is a diagonal matrix
Okay.
that just achieves this coordinate direction stretching. And when I say coordinate direction, I really mean eigen coordinates. But this is all just a roundabout way of saying if these two things are the same, for any vector x written in standard coordinates, then multiplying on both sides by p inverse, because if p is a change of basis matrix, it has to be invertible.
That A can be written in this form.
Right, that A can be written in this form. So that was really all I was trying to say, is that...
Which is to say that there's this equivalence relation, actually?
Well, it's a conjugation, really, and it is an equivalence relation somehow, right?
There exists this...
such that...
This P, such that...
and this is going to be
A
true.
relates to D by conjugation.
For all A in our representation, D2 of G, whatever, okay, there exists a D a diagonal D.
Oh, so A is not necessarily diagonal, or not.
A is not necessarily diagonal,
Okay.
but the very same change of basis matrix, P, so this is the same for all my group elements. The very same change of basis matrix can diagonalize every single matrix in my representation.
Okay.
So, let me clean this up just a little bit. Oops. Such that for all A in D2 of G, let's write this the other way around. P times A times P inverse is equal to D. P times A times P inverse is diagonal. So this last part is the diagonalizability. This unique definition of P, in other words, one P that works for them all, that's the simultaneous part. But the same change of basis can make all my matrices diagonal.
So there is a special P that does this.
Right. And that P is the basis of common eigenvectors of all of our matrices.
So that's where the basis that does this comes from.
Yep. And the other algebraic ramification of this is that let's suppose, if this is true, let's suppose I have two matrices A and B that are both part of my representation. Then that implies that I can write A as P inverse times some diagonal matrix times P, And I can write B as the same thing, P inverse times some diagonal matrix D prime or something like that, times P.
And if I want to multiply A and B together, then
Yeah.
the P's will cancel.
If I multiply A and B together, the P's cancel.
Just D prime, but the conjugation of that.
I get D times D prime.
The conjugation of that.
Right. What's BA?
So BA would be just the other way around. D. Well, the conjugation of D prime D.
Uh-huh. What's the difference between these?
Difference?
Are these two expressions the same, or are they...
Well, I mean, if A and B commute with each other, then, you know, D...
That's what I'm asking, I guess,
Oh.
is do A and B commute with each other
But
here?
where are we getting A and B?
There are any old matrices that are part of this representation. We don't know necessarily anything about them. We only know that they are simultaneously diagonalizable. What kind of matrices are D and D prime?
Well, they are diagonal.
They're diagonal.
Mm-hmm.
So when I multiply a diagonal matrix by another diagonal matrix, what can you say about that product?
Oh, well,
7, 0, 0 pi times negative 2, 0, 0, 1 half. Let's say I do this product. What am I going to get?
but when we go the other way, negative 2 times 7, yeah, okay. And because real numbers is commutative.
Yeah.
Yep.
Yep.
Okay.
So that was the really roundabout
So,
point that I'm trying to make here, is that diagonal matrices commute
is it true that...
one with another.
Is it true for any, any matrix which is equal to its transpose is...
Where are we getting transpose here?
Well, in this sense, I mean, well, diagonal matrices are...
They are equal to their transpose, but there are a lot of other matrices that are as well. Symmetric matrices.
But, I mean, is matrix multiplication between matrices that are equal to their transpose, is that... No, that's not...
No. Too much to hope for.
Okay.
But what we can say is that simultaneously diagonalizable matrices commute with one another. And in fact, the converse is also true.
It makes sense because we're only looking at the sums for the diagonal entries, the products of the diagonal.
The products of the diagonal entries, right. And again, we needed simultaneous diagonalizability so that the same P could be used to express both A and B, and it then cancels when you multiply AB and BA in the opposite orders. And so the general statement is that it goes both ways as long as all of our matrices are diagonalizable. That if A and B are diagonalizable and they commute, then they are simultaneously diagonalizable. And conversely, if A and B are simultaneously diagonalizable, then they commute one with another.
Okay.
And that's the algebraic hook here. This is why it turns out that this happens when we represent abelian
that's
groups.
what I was exactly thinking.
Is it because the group elements in an abelian group have to commute, the matrices that represent them also have to commute, and therefore if the matrices commute and are diagonalizable, then they must be simultaneously diagonalizable, so we can find a common eigenbasis. But finding a common eigenbasis, making these matrices into diagonal form, means that the representation is reducible. Not only that, completely reducible down to one-dimensional, a direct sum of one-dimensional representations.
Oh, wait, okay, so
Representations
you
on the
say
diagonal.
commute implies abelian groups?
So actually,
You mean-
it would be we'd be going the other way
around.
here. That if we're trying to represent an abelian group, we require that the matrices commute.
Oh yeah,
with
that's
one
got to
another.
follow from that.
Also, the other part we needed to know was this part. We needed to know that the matrices that are used to represent abelian groups are diagonalizable. In fact, what we'll show when we talk about the theorem of complete reducibility is that the matrices representing any group, any finite group, will always be diagonalizable. That we're never going to get deficient eigenspaces with representations of a finite group. So the diagonalizability part actually doesn't come for free. It's actually a big theorem, the theorem of complete reducibility. But with that theorem in hand, it means that these matrices must be diagonalizable, and if our group is abelian, they must commute. And therefore, every representation that we could think of writing down has a simultaneous eigenbasis, and therefore is simultaneously diagonalizable, and therefore reduces completely to a direct sum of one-dimensional representations. So the only irreducible representations of an abelian group must be
1 degree
one degree one representations.